So I graded question C on the homework, which was min-terms 4, 12, 6, and 2. And so your goal was to write an unsimplified sum of products and product of sums, and then to use a K-map to simplify both of those. So sum of products, I think people nailed that one down. If we think of our variables in this order, and we were to write hey, there we go. Thank you. Have people memorized how to do this yet? Writing out these ones and zeros? Because you'll do it like a few hundred times in this course.
You need a stamp, you've already done that.
That would be great, man. A rubber
Yeah.
stamp.
Yeah.
I should get one of those. I'm gonna do that. I'm gonna give it to Izad for his birthday too. He was so freaking out. All right, so we've got outputs at terms 2, 4, 6, and 12. And so sum of products, we just write down the min terms associated with each of these one outputs. So that's going to be A bar, B bar, C, D bar. And the 4 term will be A bar, B, C bar, D bar. That's this one. And the 6 term will be A bar, B, C, D bar. And the 12 term will be A, B, C bar, D bar. Now, how do you know if you're doing this right without going blind by trying to like read all these ones and zeros hour after hour? If I think of things with a bar as 0 and without a bar as 1, to me, when I see A bar, B bar, C, D, I see 1, 1, 0, 0. And if I convert that to decimal, I get a 12. There's my 12. When I see 0, 1, 1, 0, that binary number is 6. There's my 6. So you can make yourself a procedure for going from here directly to here, right? But doing that without knowing why you're writing these terms down is not a good strategy. So you want to be able to write the truth table and then think of this as a min term, and so it's A bar, B, C, right? But once you've done that enough times and you're comfortable with it, you start to realize that you're really just writing down the binary version of these min terms, where you put a bar over something for 0 and no bar for 1. Okay, for max terms, for a product of sums, so this is sum of products. Product of sums is going to be the product of all the rows where the output is 0. Okay, remember we work with the zeros. So it's actually the product of max terms 0, 1, 3, 5, 7, 8, 9, 10, 11, 13, 14, and 15. All of those 0 terms. So your product of sums is going to have a lot of pieces to it. In particular, since your sum of products had 4 pieces, your product of sum had better end up with 12 pieces, because you've got a total of 16 terms here. And anything that's not in the sum of products is going to be in the product of sums. They play off each other that way. So we could write F as, and we want to write a max term for each of these. And the same trick I just described, except you put a bar over something for a 1 and no bar for a 0. So this max term 0 is A or B or C or D. And remember, it's product of sums, so each of these is a sum. It's a bunch of ors. And then we product all of those together. So the 1 is going to be A or B or C or D bar. And the 3 is going to be A or B or C bar or D, and so on. And there's 9 more terms you have to write. Questions about that? So the main issue I saw at this point was some people wrote down the max terms for the 1 terms instead of the zeros. So right idea, but you ended up with 4 things. And you actually got an expression for the complement of f. Okay, so not a big worry there. All right, and then the K-maps. So sum of products, most people were spot on. Make sure it's 0, 0, 0, 1, 1, 1, 1, 0. There are a few cases where they went in traditional order instead of that correct order. So that's what your 1 terms, that's where they land. And by the way, you can kind of shortcut this as well. If I just think in terms of max terms or min terms, term 0, or rows of a truth table, this is row 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And once you recognize that pattern, if you have a truth table, you can just pick each row, right, 2, 4, 6, and 12, and just drop your 1s into those positions in the K-map. So you can shortcut a lot of this stuff once you understand how to do it this way, right? So there's a K-map for the 1s, and the covering is pretty unambiguous. That's really going to be your best cover. I could cover these 2 1s horizontally, but I'd still need to cover this one and this one. That's going to end up being a total of 3 rectangles, right? So you want as few rectangles as possible, so this is going to be your optimal cover, is just to do those 2 vertical rectangles. And this one looks like A bar, B doesn't matter, C, and D bar. And this one looks like B, C bar, D bar. So F is just the sum of those 2 products. All right, for the product of sums, again, you have to cover the zeros, not the 1s. So you're going to have a lot more pieces in your K-map. And I saw some people change the zeros to 1s and the 1s to zeros and then covered the 1s. And that gets you the correct answer, but it might be confusing on a test, especially to someone else if they haven't seen you do that. So I would stick to just writing in the zeros and then go ahead and cover the zeros for a product of sums. And this one, there's lots of ways to cover it, but the first one that really kind of screams out, I think, is this right here. Right, we almost got to believe that that's going to be part of an optimal cover. And sometimes you might cover some stuff that looks reasonable, but find out that there was a better cover. But if you can cover a 4x2, that's probably a good thing to do, because we just used up, 2/3 of all the zeros that we need to cover. And we got to cover these and these. And I can definitely wrap these 2 around, right, to cover this and this together and make it as big as possible. Let's pick up these 2 also. So let's do a 2x2 that picks up those. And then we're left just to cover these 2, but again, let's make it bigger. Pick up the ones next to it. We're double covering some of these, nothing wrong with that. So equations, we're writing max terms. Okay, so this big rectangle, A could be 0 or 1. B could be 0 or 1. C could actually be 0 or 1. D has got to be a 1. Okay, so for a max term, if your variable is equal to 1, you write it with a bar on top. If it's equal to 0, you write it without a bar. So this big block corresponds to D bar. The green 2 by 2 that's split across the top and bottom, A could be 0 or 1, so that doesn't matter. B has got to be 0, right? It's 0 here, it's 0 here. C is a 0 here and a 0 here, and D could be 0 or 1. So we don't care about A or D, we only care about B and C, and those are both 0, so the expression there is B or C. And then our blue 2 by 2, A has got to be 1, B doesn't matter, C has got to be 1, and D doesn't matter. And so if a variable is equal to 1, we write it with a bar, and we OR those. So that blue rectangle is the max term A bar or C bar. And then you combine those by taking the product of each of those sum terms, so F is equal to D bar, ANDed with B or C, ANDed with A bar or C bar. So there's a minimized expression. All right, so questions on that or other homework questions? That's basically the procedure for all of those questions. Let me talk about Lab 4. And if we don't get to programmable logic today, we'll skip that from the homework. Because there's 2 or 3 questions on programmable logic. So I may amend the homework at the end of this, but let's see how much time we spend on Lab 4. This is uploading finally. All right, so Lab 4, 2 experiments. Okay, the first one is kind of a warm-up, and the second one you're going to build a 2-bit adder. So you can add 2-bit numbers. And if you look at the supply list, there's an optional supply here, 74LSXX, as required by the design. Consider using 74LS47. Definitely consider using that. It's not really doable without that. So it's a hint here, but this is what you're going to want to use, and we'll explain why in a few minutes. Okay, so part of what you're dealing with in your lab is this little device called a 7-segment display. And it looks kind of like this. It's actually a chip-sized rectangle, and it has several LEDs inside it. And 7 of them are laid out in this pattern, and there's usually a little LED down here also. And the idea is by lighting certain combinations of these LEDs, you can make this thing look like a number. For example, if I were to light up this LED and this one and this, it looks like the number 4. And if I light up this LED and this one, it looks like the number 7. And there's the number 3, and so on. So you've got 7 segments, 7 LEDs up here. We won't worry about the decimal point. 7 segments, and we label them A through G. And by turning certain of them on, we can make this display look like it's displaying a number. So your goal when you build your 2-bit adder is it's going to display your sum using this display. So if I set one of my inputs to be 1, 0, that's the number 2, and I set my other inputs to be 1, 1, that's the number 3. Your circuit should calculate 2 plus 3 equals 5, and then it should light up these segments to make it look like the answer is 5. Okay, so it's a pretty cool circuit when you get it all done. So let's talk first of all about how we make this happen. So we've got 7 segments here. We've got 7 outputs that we need to control, A through G. And depending on your input values, let me call it sum 0, sum 1, and sum 2. So 3 inputs, and depending on the value of these 3 inputs, we want to turn these LEDs on or off accordingly. Okay, so it's a truth table with 8 rows and 7 outputs. So you could build 7 circuits, each with 3 inputs. It's going to be a really complex circuit. Fortunately, there's a chip that already does this for us, and it's called the 74LS47. And you can find the data sheet for this on engrcs.com. So go under Resources, Component Specifications, and scroll down to 74LS47. And here's the data sheet on this decoder. A decoder is almost like a demultiplexer. Okay, so as usual, there's multiple packages described in here. This is a 74LS49. This is a different version of a 47. This is the version of the 47 that we have. Okay, so 74LS47, and it's a 16-pin chip. Okay, ground goes into pin 8, power goes on pin 16, as usual. And here's the outputs, A, B, C, D, E, F, G, that go to the 7 segments of the display. And your inputs are labeled uppercase A, B, C, D, and it actually takes 4 input bits. And we only care about 3 inputs, because our sum's going to be from 0 to 6, right? So it's a 3-bit sum. But this chip actually takes 4 inputs. So it also takes a 4th bit. And we're just going to want to set that to ground. And there's some other pins here, lamp test and ripple out and ripple in. And we'll see what to do with those shortly. So here's what this thing does. It basically displays one of these symbols based on the 4 inputs, uppercase A, B, C, and D. So the first 10 of these just look like the digits 0 through 9, but then it's got some alien versus predator kind of symbols over here for the last 6 input combinations. And here's a truth table. So depending on the values of A, B, C, and D, the inputs, if they're all low, then all of your outputs are on except for segment G, right? Which is why you get this symbol. So segment G is the one in the middle. And if your input is 0, 0, 0, 1, then segments B and C are on. That's these 2 over here on the right, and it looks like a 1. So you don't really need to worry about the truth table. Mostly you just need to know that whatever 4-bit value you put into A, B, C, D causes the output to look like one of these 16 pictures. And the ones we care about, 0 through 6, right? If you put in a value of 4, it's going to display a 4. If you put in a 2, it'll display a 2, and so on. These other inputs you want to be a little careful with. So in all of these, this LT bar input has to be high. Okay, that's a lamp test. If you pull it low, all your segments turn on. That's how you check to see if the bulbs are all working. So make sure LT bar is tied high. And then RBI should not matter. So you can leave that floating. And BI, I would, is that an input? I would set that to high also. Because if you set it to low, then you get different behavior. So tie BI to high, tie LT bar to high, and RBI doesn't matter. You can tie it high if you want. And with those three things set up and power and ground connected, you feed an input to ABCD and it lights up. It sends these 7 outputs accordingly, and you connect these to the pins that drive the pieces of your 7-segment display, which we still need to talk about. So this 74LS47, you can work with this by itself. Forget about adders, forget about switches, forget about all of that, right? Just wire up a 7447, connect the outputs to one of these 7-segment displays, set these 2 inputs accordingly, and now just connect some wires to ABCD and plug them into either ground or 5 volts and see what the display does. Okay, it's a really good first exercise to sort of figure out exactly how this chip works. And you should see that if you connect these up to power and ground, whatever number you've spelled out with those 1s and 0s causes the display to show one of these pictures.
What's going on with the RBI bar?
This one?
It's high just for 0, and other than that, it's...
So if it's high and your inputs are all 0, then you get this 0 coming out. That may be a typo. I would tie it high just in case. It shouldn't make any difference as long as lamp test is high. But since it doesn't matter in any of these cases, in this case it says high, I would tie that high just to make sure, but I think that's a typo.
And those are just don't cares?
The X's are don't cares.
Okay.
Yeah, so they use X's instead of dashes.
Gotcha.
All right, so yeah, tie all 3 of those high: BI bar, RBI bar, and LT bar. And that's what's inside that chip. So that's what you end up with if you built it yourself. That's why it says consider using this chip instead. All right. So 2 experiments. The first experiment is working with the 7-segment display. So it's a little gray chip. You can see the outline of those 7 LEDs on top. And if you look at it from the top, this is pin 1, pin 7, pin 8, pin 14. It will have some missing pins. That's okay. It doesn't actually have 14 pins coming off, but you count them as if they were all there. So it's pin 1 to 7, 8 to 14, even if pin 5 is missing, right? It still gets counted. And this is what it looks like electrically. So pins 3 and 14 normally get pulled up to 5 volts through a resistor. And pins 1, 13, 10, 8, 7, 2, 11, and 9, you can connect those to ground to turn one of these segments on. So we always connect 3 and 14 through a 1K resistor to 5 volts. And now if I connect pin 1 to ground, segment A should light up. If I connect pin 13 to ground, segment B should light up, and so on. So there's 3 things to do in experiment 1. Experiment 1 says calculate the maximum combined forward current through all 8 diodes. And that's ambiguous. There's a few ways to interpret that. But I would think of it like this. What's the most current that could be flowing from our power supply to ground through these diodes? So think about it, right? The goal is not the answer, it's the process of analyzing it. It's like a koan. So depending on which ones I connect to ground, where does current flow and how much current flows? If nothing's connected to ground, there's no current. If I connect one thing to ground, all the current will flow through one LED. How much current is that? If I connect 2 to ground, how much current flows through each LED? What's the total current? So play some games with that mentally, right? And write something up for part 1. Part 2, you want to design a circuit that lights up segments A, B, C, E, F, and G. In other words, everything except the bottom segment. So it's going to look like a letter A. And it's just a matter of connecting some of these to ground, and some of them are not connected. and then go ahead and build that circuit and test it out. And when you power it up, you should see the letter A displayed. All right, so that's a warm-up with the 7-segment display, and that has nothing to do with the 7447. Okay, this is just the segment display by itself. All right, part 2, this is your 2-bit adder. And like lab 3, you got to be really careful what you do here, because a lot of people will skip over pieces of this and you lose a lot of points. Okay? So there's actually a few totally separate independent things that you're doing here. Okay, your goal is to make a 2-bit adder. So you're going to have 2 switches for your first number, 2 switches for your second number, a total of 4 switches. And by toggling those in, you get your answer out on your 7-segment display, your sum. Okay, so what do you want to do? System diagram. Okay, list the input variables and the output variables for a 2-bit binary adder. So 2-bit adder, here I'll show you a system diagram, and then you won't have to think too hard about that. There's a block diagram view, and the operation is something like this. Right, it's taking a 2-bit number, B1, B0, and a 2-bit number, A1, A0, and it's adding them together numerically and getting a 3-bit sum, S2, S1, S0. So your system diagram should look something like that. All right, so that's part A. Part B, truth table based on what you drew in part A. So what's the truth table going to look like? B1, B0, A1, A0, S2, S1, S0. 4 inputs, 3 outputs. 16 rows, 3 output columns. Okay, how you fill this in depends on your analysis of what addition does, right? But I'll start you off. That's your first row. All right, you can do the other 15. All right, so truth table based on that. Okay, minimized output functions in either POS or SOP using a K-map. So you're going to do a product of sum or sum of products, depending on which you choose. You're going to put it into a K-map. You're going to minimize it. You're going to end up with 3 expressions. S2 equals, S1 equals, S0 equals. And each of these will be a sum of products or a product of sums. Okay, this is all doing stuff you've already done for truth tables, turning them into equations. All right, that's the first piece of experiment 2. There's a totally separate second piece, okay, which is to actually come up with a schematic, a wiring diagram, and implement it and test it to do addition of 2 2-bit numbers. And here's why it's a totally separate piece. If this were any other circuit, you would have these 3 equations. You would start drawing pictures of AND gates and OR gates and inverters to implement each of these. And it's a really, really big circuit you're going to end up with. And it's not the best way to do this. Okay, so there's a totally different approach. And if you're going to use this different approach, you can't just jump from here and these equations to a circuit for this other approach. You've got to develop it. You've got to explain in your report what you're doing. So you come up with these 3 equations based on the truth table, but that's probably not what you want to use to actually build your adder. What you really want to do in the end is a half adder and a full adder. and your carry out from here goes into there. Your carry out here becomes a sum bit. There's your sum bit. There's your two inputs to each adder. So A0, B0, A1, B1, sum 0, sum 1, sum 2, carry out, carry in, carry out. And it's a half adder, so there's no carry in. But avoid the temptation of going from truth table equations and then suddenly putting this in your lab report. This has nothing to do with those equations for S1 equals S2 equals. Okay, so it's a little, it seems a little wasteful, but you're going to do the truth table, you're going to fill it in, you're going to write down the expressions, you're going to use K-maps to minimize, you're going to come up with simplified expressions for S0, S1, S2, but then you're not going to use any of that to actually build your circuit. Okay, so that's all kind of exercise to see if you didn't know about half adder, full adder, right, what kind of equations would you need to implement? S0 equals this, S1 equals that, and so on. But look at those equations and decide, do you want to actually implement those? And they're probably going to be way too big to look like something you want to actually build. So now in your report, put a break, start a new section, alternative design, right? And it says in here, hint, consider using standard adder and half adder design. Okay, and part D, which is what we're talking about, using the results from part C, that's your equations, or your research into possible designs. Okay, so we're making a break here. Down to part C, we came up with equations for each of those S's. Now you're going to say alternative design and talk about the half adder, full adder approach. So what is a half adder? Put in the truth table. Describe what it does. What is a full adder? Put in a truth table, describe what it does. Put in a block diagram. We're going to put these together like this. This will implement a 2-bit adder using this half adder and this full adder. Now you've got to implement these things. How do you do that? Write a truth table. Write down the sum of products. Use a K-map to simplify. Draw a wiring diagram. Okay, you got to go through all those steps. If you do that, you end up with a way to implement this and this, put them together, either in one big diagram or, label this output and label an input on this diagram with the same label or something. Put on pin numbers, part numbers, and then you've got a wiring diagram based on this. Build that, test it. Is that clear? Here's what I hope I don't see, right, is all of this stuff, S0 equals big long expression, S1 equals this, S2 equals this, and then a wiring diagram for this with nothing in between. Okay? That's a big gaping hole there. It's like, wait a minute, this circuit has nothing to do with these equations. Where did this circuit come from? Okay, so make sure you explain that, make sure you develop it. Okay, alternative design or a different idea or something like that. Talk about this. And then develop each of these. Truth table, equations, simplify, wiring diagram, block diagram, put it all together. Make sense? All right, so you do all of that, and when you're done, you've got this thing built, and now this goes into your 74LS47. This is the A, B, and C input. Your D input. So all of this goes into your 74LS47. Your A, B, and C inputs come from your sum. Your D input goes to ground because this wants a 4-bit input, but our most significant bit is always 0 because our values are 0 through 6. And then this goes to the 7-segment display. So this part you can just draw with a box. Call it 74LS47 and just list the inputs A, B, C, D, and the outputs A through G. And you don't have to put in power connections and things like that, but we don't have a standard symbol for a 7-segment decoder, so you can just draw a picture of the chip and label it. But then all of this, you're going to have AND gates and OR gates and inverters and things like that. And you're going to have switches, right, going up to 5 volts and ways to pull them to ground, and you're going to label them and so on and so forth. So it's a long lab, okay, but you can break it into pieces and make it pretty manageable. So one piece, like I said, is just to play with the 7-segment display. That's experiment 1. Another piece is just to play with the 7-segment display and the 7447 and get a handle on how setting those A, B, C, D inputs affect the display. And that's a fun thing to do anyway, as much fun as you can have in the lab at least. It's a fun thing to do because you get to, you know, display things. And then you can build this adder and forget about all of this stuff. Just pop 3 LEDs on there, right? And add 2 and 3 and make sure your output says 1, 0, 1. And then add 2 and 2 and make sure it says 1, 0, 0. And get this whole adder part working correctly. Now you've done some work with this piece, right? And now you got this piece working. And once those two work, now you just took them together. Yeah.
I don't know if I missed something, but is that adder, is that a chip, or that's we have to use AND gates and OR gates?
So you're going to use AND gates and OR gates to make a half adder and a full adder and put them together to make a 2-bit adder.
Cool.
Yeah, so write down the truth tables, equations, minimize, wiring diagram. Okay, just keep asking yourself, right, have I skipped anything in my write-up here? Right, logically what your write-up says should flow, right? If you spend an hour getting from one step to the next, there's probably going to be something in your lab between those 2 steps, right? Saying how you got from here to there. All right, so implement, test, and demonstrate, get a sign-off. Cover sheet, lessons learned, new experiment, keep the new experiments coming. And that's your lab 4. So questions?
No test plan?
Never hurts to put in a test plan, but it doesn't actually ask for one. But the easiest way to describe a test plan might be, you know, try all combinations of A and B and make sure the sum is right. So that's probably good enough. Let me make a suggestion. When you lay this thing out on a proto board, and you've got your block of switches, and you've got, let's say, some LEDs, it's really helpful if you lay these switches out. So for example, this is A1 and A0, and these 2 switches over here are B1 and B0, and this is S2 and S1 and S0. If you physically lay them out in this way, your testing is going to be a lot quicker. If you flip these around and then you do 1, 0, 1, 0, you've got to mentally in your head say, okay, this is B0 and B1, so this is the number 1 and this is the number 2. That should add up to 3. And if you set up your LEDs to be this, right, then you got to mentally say, okay, so a 3, that should be on and off and on, right? And you can spend a lot of time trying to figure out if your circuit works correctly or not. And worse, your circuit might be working correctly and you're misinterpreting what it's doing, and you get frustrated and you rip your wires out and start over, right? So it's really easy if you think about it ahead of time. Lay your switch out like this. 2 rightmost ones, use that most significant bit, least significant bit. 2 leftmost ones, most and least. Lay out your LEDs in order, most significant, least significant. Guarantee it'll save you time. Okay. I'm not making it a requirement this time, because inevitably some people won't do it anyway. But it will definitely help you out. Right? Having these switches on opposite ends stops you from accidentally hitting one when you're hitting the other, and so on and so forth. So that's a suggestion. All right, good on lab 4. You notice there's no traffic light in this one. So we got a break. All right, we have 15 minutes. Let me start talking about programmable devices, because this is actually a pretty cool concept. So a random function, suppose you've done a truth table and some other stuff and you've decided this is the function you want to implement. And we talked in the beginning of the course, we reviewed a convenient way to build this circuit on paper, which was take your inputs, run them vertically, feed each of them into an inverter, and run that next to the uninverted input. And then take each of our product terms, bless you, and assuming we've got 3 input gates available, just connect this up to the correct input. So A, B bar, C. And here's another gauge. And I'm just going to get lazy with my drawing. So A bar, B, C bar, and one more AND gauge. And this is A, B, C bar. And then we just take all of these and we feed them into an OR gauge. And there's our output X. We've done this in 120, we've done it again in here. Everybody's okay with this, right? Now suppose I had a different function. Suppose what I really wanted to implement was X equals ABC or A bar, B bar C, or A, B bar, C bar. What do I have to change in this picture to implement this new function? Do I have to erase the whole thing and start over? Just the connections. So ignore the dots that are up there. Let me use bigger dots in red. And suppose I do the following. That's A, B, C. This is A bar, B bar, C. And this is A, B bar, C bar. There's my new function X. And any function, in this case of 3, any sum of 3 products, I can design that with this diagram by just changing where my connections are over here. And everything else is exactly the same. So somebody very clever had the idea, what if we built a piece of hardware that basically looked like this, but let you, after this piece of hardware was in your possession, let you control which connections you made over here between these inputs and the inputs to these AND gates. You could customize this to implement this function or any other function that you wanted. So these things exist, they're commercially available, they're generally called programmable logic. And this one in particular is called a PAL, which is programmable array logic. And here's a picture of what a PAL looks like, and there's some shorthands we can use to draw these things. So this isn't sacred. I'm drawing my input A, and I've got two things coming off. The thing coming off the triangle is just A. The thing coming off the little circle is A bar. So it's a slightly more succinct way to draw these inputs. And I don't know, let's give ourselves 4 inputs. And instead of drawing an AND gate with a bunch of lines coming across, I'm going to draw a single AND gate symbol. And I'm just going to have one line coming across. And I'm going to allow you to put multiple marks in here with the understanding that we probably have 4 lines coming into this AND gate. But I don't want to keep drawing 4 lines over and over and over again, so I'm just going to draw a single line with an AND gate symbol. And I'm going to do a bunch of these. So I don't know, we'll do 6 of them. And instead of drawing 6 lines from here into an OR gate, I'm just going to draw 1 line, and we understand that's actually 6 lines. So each of these are going into one of 6 inputs on this OR gate. So this output X is this ORed with this, ORed with this, right? And it saves me from having to make the OR gate symbol like that.
Are we able to do that when we're doing our lab reports, or?
You're able to do it if you're doing a programmable logic device like this, but that's the only time.
Gotcha.
So example, X equals AD or B bar CD bar or A bar D bar. All right, instead of using X's, instead of using dots, I'm going to use X's to indicate a connection, just because it's a little easier to draw. So my first AND term, I'm going to take the AND of A with D. I'm just going to put a little mark here and a little mark here. And this says A is going into my AND gate and D is also going into my AND gate. And the second line, we want B bar, we want C, we want D bar. And this third line, we want A bar, and we want D bar. And that's enough information to describe a circuit that implements this function X. And we might have multiple outputs. So I might have another OR gate here and call that output Y, and maybe we want Y to be AB or BC or CD or AD. We'll leave off the AD because I don't have enough lines. So AB, right, I could put a connection here on A and B. I could put a connection on B and C, and I could put a connection on C and D. And now Y is AB or BC or CD. And if I actually had this physical hardware, and I had, you know, multiple wires coming across and so on, all I got to do is somehow make a connection between these horizontal and vertical lines in the right places, and bingo, I've got a piece of circuitry now that generates 2 outputs based on these equations. And of course, we can write computer programs to take something like a truth table and turn it into a set of equations like this. And from there to figure out exactly where we want these connections. So the next question is, how do we physically implement this? How do we actually create a device that we can somehow control these connections between these lines and these horizontal lines? So what is a fuse? We don't have fuses much anymore. Anybody have fuses in their house, their apartment? It's usually circuit breakers, but sometimes the older ones have fuses. So a fuse is a piece of metal that when you run too much current through it, it melts. Okay, so why does it melt? Well, current, voltage, multiply them, you get power. Power comes off as heat. You heat up metal enough, it'll melt. So a fuse is a piece of metal made out of a material that melts at a very low temperature, a couple of 100 degrees maybe. And you tune it so that if you send, say, 15 amps of current at 120 volts through this piece of metal, it'll get so hot that the metal will melt. And when it melts, it stops conducting electricity because there's a gap in the metal. So you put a fuse in your electric panel at home, you got power coming in from the street, lots of current potentially. You run it through wires in the wall to your lights and your outlets and so on. Well, without a fuse, if you put too much current through those wires will melt. And if the wires melt in the wall, it's really expensive to replace them. So before the electricity gets to those wires in the wall, it goes through this fuse, and you set it up. You know that these wires can handle 20 amps of current. You set up this fuse, so if it draws 15 amps, it melts, and it protects the wiring in the house. Okay, well, you put little tiny fuses inside this chip, and it's exactly the same thing. You start off with connections between every vertical line and every horizontal line, and those connections are little fuses. And now one by one, if you don't want a connection, you run a lot of current through that fuse and you melt it, and it breaks the connection. And the fuses you didn't melt, those are the connections you have left. So that's how you program this device. So this is generally called programmable logic. And this is, a little 20-pin chip. You plug it into a programmer, and you tell it where you want the connections to be, and it will go through, it will send current through each of these fuses in the right way to melt the ones you don't want, and leave you with a chip that's been programmed to implement your functions.
Reprogrammable chips.
That's harder, right? So these are one-time programmable if they're fuse-based, unless you want to have fewer connections, right? But in general, once you blow a fuse, you can't get that connection back. But, so these were the old version of these things, and they're still available. They're very inexpensive. But using various semiconductor properties, right, we can make reprogrammable versions of this. And it's in some ways similar to how a flash drive works. Right, a flash drive, you can write ones and zeros and disconnect it from the power, and it remembers what those values are. Okay, it's changing the material state of things at a quantum level of some sort. Same thing you can do with this to get reprogrammable devices. But we still use this fuse model even if it's not fuses working underneath. So we draw an X to show a connection, and if we don't have a connection, we just have wires crossing with no symbol there. So there's no connection between C and this line, for example. But there is between D and this horizontal line. All right, so I'm going to take that corresponding homework off the table for Thursday because I want to say some more about programmable logic. So you can ignore questions, I think it's the last two. So questions 10 and 11, you can save those for next time. But all the other ones still stand. So I will edit this accordingly. All right, so work on the other homework questions, get a start on the lab, bring questions on Thursday. We'll finish talking about programmable logic. We'll talk about compressed truth tables. We'll talk about a few more of these medium scale devices. And then we're gonna go ahead and start talking about circuits that have memory. And that's gonna open up a whole new area of circuits we can design. All right, so I'll see you next time.